Is Jupiter a failed star? And if it actually did become one, what would happen? The idea that the planet Jupiter should be regarded as a failed star, or a celestial entity whose mass nearly permitted it to ignite nuclear fusion reactions, but failed to do so, is still occasionally made in astronomy papers, especially on the web. What about this statement is true? Let's go together and find out. This is most likely a belief that dates back to the discovery that Jupiter radiates around 1.5 times as much heat into space as it does from the Sun in the late 1970s. This may have given rise to the theory that the planet formerly generated heat through nuclear fusion, which would have then been partially conserved by thermal inertia. However, if this were the case, how come Saturn, whose mass is more than 3 times that of Jupiter, emits up to 2.5 times as much heat as it absorbs from the Sun? In fact, it is improbable that a celestial body of a given mass would radiate more heat than a body of a larger mass. In actuality, there is another explanation for the phenomenon. Below the gaseous atmosphere, we discover a layer of liquid hydrogen and helium, one of metallic hydrogen, and a solid core whose composition is still unknown. Jupiter's internal structure is composed of these layers. Because it is heavier than hydrogen, helium has a tendency to fall in the uppermost layer. Heat is produced as a result of the release of gravitational energy. Since Saturn is further away from the Sun and hence colder, there is less stirring caused by thermal movements, which allows the helium to descend more readily. Consequently, the planet emits heat with a higher intensity. Jupiter is, in essence, a pretty common planet. Failed stars are something quite different. But are we actually certain? Is the gap between a large gas planet and the tiniest star we are aware of truly so wide and impenetrable? Although there is a minimum boundary, below which we speak of a planet, and a maximum threshold, beyond which we speak of a star, in fact, these boundaries are still being defined, and it is by no means straightforward to understand the true nature of a celestial object. However, we do know that EBLM J0555-57b, a red dwarf that is a member of a triple system and is roughly 630 light-years from Earth in the constellation Pictor, is the tiniest known star in our galaxy. Such a star cannot generate high pressures within due to its small mass, less than half that of the Sun, therefore nuclear processes that are sparked in the core only yield a small amount of energy. These stars have exceptionally long lives due to the extreme smallness of their combustion. The shortest spans are expected to be on the order of hundreds of billions of years. Since the universe is thought to be about 13 billion years old, no red dwarf has yet gone extinct. The incredibly small surface areas of these stars make radiation losses of the remaining energy very sluggish. Thus, even after all the hydrogen has been used, a red dwarf will continue to radiate a weak light and gradually vanish from view, having by this point changed into an ice, invisible black dwarf. According to current stellar evolution models, EBLM is a fairly tiny star with barely enough mass to start hydrogen fusion in its core. Its 120,000 kilometers diameter is even less than Jupiter's 143,000 kilometers equatorial diameter, which is not nearly a tenth of the Sun's. However, it sparkles and produces light. So, your first thought is, why hasn't Jupiter, which is even bigger, turned into a star instead of staying a planet? The quick response is this: despite Jupiter's enormous size, it does not contain enough mass to initiate nuclear fusion and convert the hydrogen inside of it into helium. In actuality, for this to occur, a substance must be both big and hot enough for individual atoms to overcome repelling forces and compress. And if this little red dwarf is able to ignite its nuclear furnace, it is because, despite its small size, it has a mass that is approximately 85 times that of Jupiter. This mass is the bare minimum necessary for a gas globe to get compressed to the point where nuclear fusion occurs. But hold on a second, how is it smaller and 85 times as large as Jupiter? And here, there is only one immediate explanation: it succeeds because of its enormous density of 188 grams per cubic centimeter. Do you want to know why we refer to this value as being incredible? Well, it will do to simply consider that while Jupiter's density is extremely low, only 1.3 grams per cubic centimeter, our Earth's density, which is also the highest in the solar system, is only 5.5 grams per cubic centimeter. All of this can only mean one thing: Jupiter could only become a star if its mass suddenly increased by a factor of 85 over what it currently holds. Is there any possibility that this could occur? Absolutely not in the real world, but as we'll discover in a moment, in the science fiction universe created by the great Arthur Clarke, it actually did happen. However, Jupiter might try to become a brown dwarf, which is a much more likely path to becoming a star. Specifically, a substellar object whose mass is sufficient to cause the nuclear burning of deuterium, a lighter isotope of hydrogen, but insufficient to cause the nuclear burning of hydrogen. The exact limits of what constitutes a brown dwarf are still up for debate, although astronomers generally agree that they range in mass from 13 to 80 times that of Jupiter. Brown dwarfs are objects that may resemble planets but are actually stars, since they form straight from a molecular hydrogen nebula as opposed to from the buildup of material in a star's disk. 13 Jovian masses are the minimal mass limit below which one can speak of a brown dwarf, at which point deuterium burning starts. On the other side, lithium fusion also occurs past 65 Jovian masses. However, due to the modest amounts of deuterium and lithium present in a brown dwarf, the amount of energy that can be produced is extremely limited, and these celestial bodies will eventually cool slowly and gradually. We are aware of brown dwarfs with surfaces that are as hot as 2000 degrees Celsius and others that are clearly older and barely reach 200 degrees Celsius. In other words, Jupiter would need to just grow its mass by 13 times if it were content to settle with becoming a brown dwarf. It would also start to radiate heat and light, albeit in very small amounts, gradually warming the area around the planet. Was it possible? Again, the response is no. Indeed, where might we locate 12 more huge planetary bodies like Jupiter? But as we just indicated, Arthur Clarke left us with something to say about this. Do you recall what was said here? Jupiter truly changes into a star in the novel 2010, Odyssey 2, which served as the inspiration for the subsequent film 2010, The Year We Make Contact, albeit with the aid of billions of alien monoliths that push the planet's density above the threshold. As a result, the formerly gaseous planet starts to emit energy, and it is because of this scientific marvel that Jupiter's 4 satellites abruptly transform into planets fit for human habitation. Of course, this is pure science fiction, not least because a rise in Jupiter's mass would have unfavorable effects on the rest of the solar system. Assuming we have increased Jupiter's mass by 85 times, let's try to identify which ones they are. Then, let's start the nuclear reaction. It is also important to note that doing so would not, contrary to popular belief, cause a disproportionate growth in size. The diameter would actually only grow by 20% as a result of the components being compressed toward the center. As a result, we would obtain a red dwarf with a diameter of 170,000 kilometers and a luminosity 300 times lower than that of the Sun. However, because Jupiter is 4 times farther away from us than the Sun, the increase in energy we would experience on Earth would be only 1,000th of what we currently receive from the Sun. Practically, there would be no difference in our temperature. Instead, there would be clear repercussions for the star's brightness, which would be 80 times brighter than the full moon in our nighttime skies. This implies that for significant portions of the year, the night would vanish. And since they wouldn't be able to adequately hunt or conceal, this would have a significant impact on higher animals' nighttime behaviors. The balance of the marine ecology would change as phytoplankton would suddenly be free to flourish unhindered. Only a few times a year would stars be visible, and neither would it be possible to observe the stars from the ground. Some bird species would also stop migrating at night. All of this, however, would be insignificant in comparison to the disastrous gravitational alterations brought on by Jupiter's abrupt conversion into a star. The alterations to the planet's orbits, which would not be felt for several decades, are not the immediate threat. Rather, it is the havoc that the immense mass of the red dwarf will bring to the delicate balance of the asteroid belt. In actuality, Jupiter's gravitational pull at the moment governs and holds the asteroid belt together. The billions of objects that make up the belt, which today orbit the sun like tranquil herds of bison, might change into a chaotic swarm of mad animals if Jupiter's mass were to expand almost 100-fold. All of their moons would be destroyed and dispersed as many would be drawn toward the outer solar system and collide with the remaining gas giants Saturn, Uranus, and Neptune. Others would be aimed for the inner solar system, where they would bombard and once more turn the rocky planets, including Earth, into formless, practically liquid masses. The strokes of this cosmic billiard gone mad would destroy all the larger objects in the solar system, and eventually the remaining planets would either be expelled or redirected into far broader orbits that could circle the common barycenter of the two stars. Naturally, all of this would happen if Jupiter's transition from planet to star occurred instantly. If the solar system had already developed into a double star system, things would be different. The formation of every planet and the evolution of life would have followed different patterns in that scenario. And we most likely wouldn't be discussing it right now. Therefore, Jupiter is not a failed star. Even as a tiny brown dwarf, it never had the tiniest chance of becoming a star and never even came close. It was never meant to be one better for us, then don't you agree? Let us know in the comment section.